again. I'm sharing. I think just sharing again. Screen one, share.
Yeah, now it's coming. Yes.
Oh,
fine.
now it's coming. All right.
Yeah.
I think I deleted for some reason. Yeah.
Right.
Okay. So as introduced, I, my university is located in Adelaide, Australia. So it's a very nice city. So you're all welcome to visit us at some stage, if you have opportunity. So let me just move to the next one because you didn't see them before. So why we are doing this research? What is our motivation doing this research? So I think in Australia and similar in many other countries, there are large amount of cars being running on the road every day, and then cause a lot of issues um, of the tires. So in Australia, there are about 56 million tires reach their end of life every year. This reach very large quantities. However, this only a very small percentage was recycled, and a large percentage, about 32%, was exported to other countries in the past, and this has caused some significant problems recently, because now a lot of countries refuse to take um, the end of tires from Australia. So this caused a big issue, and this number percentage has keep declining. And if you look at disposal to landfill, the ratio is very small. It's less than 20%. And the remaining about nearly 50% of tires is either unknown or unverified on disposal in the landfill and on the mining side. So there's a big problem. And also the disposal of the tire is not biodegradable and cause a lot of environmental problems, such as trapping water, breeding ground for mosquitoes, and consuming air space in landfill. Also has caused pollution problems to the surface and groundwater, and also may cause some fire accident as well. So a lot of issues with this tire problem. Okay, so in order to overcome these problems, I will try to find out some different ways or alternative ways to reuse these recycled tires. So this project is about creating a new concrete materials called Crumb rubber concrete, CRC. Just try to using some recycled tires as partial replacement for its aggregate. So this topic is not new. We all know the recycled using recycled materials, especially recycled tires, for the concrete replacement. It is an international issue, and so far, the huge amount of research on crumb rubber concrete, always say CRC, has been carried out. A lot of papers. If you search the internet, huge amount of papers being published. However, if you look at detail of these papers, most of them still limited at the laboratory level. So really not many or even nothing on research really touched the practical applications of using crumb rubber concrete. So that's why the work was really most limited to at the research laboratory level. So that's why in this today's presentation, I'm more focused on some practical applications of using crumb rubber concrete. Okay, so our research just aims to show reinforced crumb rubber concrete is an economically viable and also sustainable alternatives to the conventional reinforced concrete structures for residential construction. So this research will provide a tire industry with a viable market for the end-of-life tires, and also for the premix concrete industry with the green products for the residential construction market. Because now every country has some policies about zero carbon emission in next few years. In Australia is 2050. So that's why all the concrete or construct industries are facing a great pressure from the government policies to adopt green concrete materials. So in this particular project, we have been working with 5 industry partners, which are listed here, and also we're working with between 2 universities. So how to recycle waste tires? So this slide shows you the procedures of recycling waste tires, which has been done by a tire circle company, which is one of our industry partners. So you can see from these figures, first they're collecting and transporting the waste tires to the factory, and then they're sorting out different type of tires. And after that, they start the shredding procedures, And then after shredding to the small pieces, then to remove inside the steel. Of course, there are a lot of people researching on using the recycled tire steel as in reinforced concrete as well. That's different research topic. So after remove those inside steels, and they have to do some further grinding to make them as a crumb rubber, very small size, normally about they have different size, but it's normally about from 0.5 up to about 3 or 4 millimeters. Okay, and finally, they need to do some basic testing to make sure it's consistency of their materials. So in our research, we're trying to use recycled tire waste in concrete as partial replacement of sand. So the current concrete market is about 24 million cubic meters per year in Australia, probably in India and some other countries even more, because Australia is not a country with a lot of construction products going on. In our testing results, we find out that it's up to 20% by volume of sand can be replaced by rubber. So that's about 70 kilograms of rubber per cubic meters could be used in concrete. So based on these calculations, it's about 1.68 million tons with tires could be recycled based on this calculation. And so there is a big potential for the construction market using recycled tires for the construction. So this diagram shows that is the tire after shredding we got from our industry partners, and this is normal sand, and that is crumb rubber concrete we made from this the tires. Okay. So through 10 years of research, we kind of get a pretty good understanding of the crumb rubber concrete or CRC performance, such as we know the compressive strength will be decreased while you increase the percentage of rubber. So this is affects now. Everyone know about these results, compressive strength. So when you use the rubber up to about 30 or 40%, there is a sharp drop of compressive strength. So therefore, crumb rubber concrete probably is most suitable for structures that do not need very high strength, like residential construction. Very interesting, our research also found out the flexural strength of concrete was not really affected by the inclusion of rubber. So although there's a sharp drop of compressive strength, but the flexural strength not really that significantly reduced at all through the 3-point bending test of a lot of concrete slabs. So that's very interesting finding. So even when the compressive strength was reduced significantly, say 20 or 30 or 50%, but the flexural strength still quite inconsistent. So therefore, we find out crumb rubber concrete probably is a very good candidate to be used for reinforced concrete slabs. So that's why our research is more focused on the concrete slabs. Okay. So these photos show the construction procedures for the 2 concrete slab we constructed using the commercial contractors, and we have constructed 2 slabs side by side. One is normal reinforced concrete, and the other one is crumb rubber concrete. We also have done a lot of testing of the composite slab in our lab, and we also apply some crumb rubber concrete in our laboratory entrance as a ground or ground slab. And this side by side, so this one side is normal concrete, and the other side is crumb rubber concrete. So I just want to say one more thing. Really, in the past few years, I saw a lot of research work on crumb rubber concrete, and a lot of people try to increase the compressive strength of crumb rubber concrete and introduce very expensive nano materials. So I don't think, although you can publish papers and everything, not a problem. Personally, I don't think there is really a research significant or necessary for this kind of research, because crumb rubber is kind of cheap material, recycled. And if you're using very expensive nano materials, just try to increase compressive strength, there's not really much practical meanings of doing this kind of research. So I thought it's better to accept the fact that is compressive strength of crumb rubber concrete is not very, very high, and we can apply those products in some structure element which do not require very high compressive strength. This is just my some personal opinion on that. So in the next probably 20 minutes or so, I'll provide some more details of a few crumb rubber concrete projects carried out by our team. I don't have time to cover everything, just a few important points what I want to discuss with you. So the first one is we look at some basic mechanical properties of crumb rubber concrete. So before making crumb rubber concrete, we have researched on the rubber size effect because we got all different size from the manufacturers. So they could have very large size as rubber chips. The size can up to 10 to 25 mils. They could be replaced on the coarse aggregate. I also have the ground rubber. So that is the one I talked about before. It's around from 0.5 to 4.75 millimeters. So these are the major crumb rubber we used, or even smaller size on crumb rubber. So it's 0.5 to 1.5 mils. We did use both of them, but in the end, actually, we find out a bit small size is better. And also, they have even smaller size, like say, running from 0.15 mils to about 2.36 mils. Although you have very, very small size crumb rubber, but we found out from our research, actually, the results was not really that good if you're using very small size. So I'll show you some more results later. Okay, so this just ICM analysis showing the crumb rubber concrete. So this one are the rubber powders particles. And you can see that they kind of bonded with the cementitious materials. So although I say the size was varying from very small 0.15 to 4.7, as what I said, we found out the best probably optimized size for our research is from 2 to 5 mils, which is around this range. Yeah. So that is good news because when you make the rubber smaller, and the cost will be higher. So make them smaller, cost will be higher. So now if we can use a larger size, I'll give you the good results. It can produce some cheaper products. Okay. So this diagram show us the change of mechanical on the unit weight change. You can see when you increase rubber contents up to about 50%, there is a reduce of the densities of concrete. So you can make a reinforced concrete materials actually was lighter when you use more crumb rubber. So this is one of the advantage using crumb rubber in concrete. And this is the compressive strength. You can see when you use 30% or even more, there is a sharp drop of 28 compressive stress. It could drop from about 65 megapascals to about 20 or 30 megapascals. So that is an issue for the compressive strength change. This is tensile strength also has a reduction, but actually, as what I said earlier, although the flexural strength probably reduced, but if you really test the samples of concrete slab, we find out there's no reduction at all for the flexural strength. So that is modulus of elasticity. Of course, it's reduced as well. It's not as significant as the compressive strength, but there is a reduction. So that is, sorry? Yeah. Okay. Another thing is an advantage of crumb rubber concrete is the impact resistance. This is also well known as well. You can see if you increase the contents of rubber, there is a big sharp increase of the impact resistance of rubber. So that's why another advantage using crumb rubber concrete could be used as a protective structure. So if you have some protective structures against impact loading like bombing or something, there are advantages there for crumb rubber. So next slide just show you some more details about a drop weight impact testing. Sorry. Everything is okay or? Yeah. I heard some background noise. Yeah, okay. So we did some drop weight impact testing based on ACI 0544. You can see for this testing, so each disc had a diameter of 150 mils, as shown in the diagram, and the thickness was 50 mils. And we have a steel cylinder was repeatedly dropped from the vertical height about 200 millimeters, 20 centimeters through the hollow steel tube. And the total number of blows was required to split the concrete specimens into two separate halves was recorded. So that is the result. You can see the normal concrete and the crumb rubber concrete with different percentage. You can see the improvement when you use more crumb rubber concrete for the failure pattern of these samples. And this one shows the number of blows. You can see the average, the number of blows at failure. Where you have a large number of crumb rubber concrete, there is a significant increase of the number of blows. So that is very good about impact resistance for the crumb rubber concrete. And another properties we tested was we look at some stress strains performance. So this is summarize the mechanical properties of crumb rubber concrete. We can see the good things about that is a very high ductility. If using crumb rubber, the improved ductility of the materials, and got very high damping ratio. So got very high energy absorption and higher toughness compared to normal concrete, and have low breakness index and high impact resistance, and also relatively low weight. So these are all the good things about crumb rubber concrete. And the major bad things about crumb rubber concrete is low compressive strength and low tensile strength. We don't say it's low fractional strength, but fractional strength is okay, but it's low modulus of elasticity. So the weakness was deteriorated of the mechanical properties, but good thing is about ductility, energy absorption, and also impact resistance and low weight. And in addition to that, we also try to find out a stress strain curve for crumb rubber concrete, because without this curve, you cannot doing the finite element analysis, and you cannot give your proper design formula. So this work has been published with a lot of citations in I think in the construction building materials. So we have developed a modified material parameters to consider the percentage of crumb rubber concrete, and this formula can predict the failure pattern of crumb rubber concrete very well when compared to different testings. Okay, so that is some testing results, and based on that, we have found this formula. So the shape of the stress strain curve for crumb rubber concrete was similar to the normal concrete, and the slope of the descending part of the normal concrete is higher than that for crumb rubber concrete. So you can see this. The red color is normal concrete, and these all other colors are crumb rubber concrete. So that is a difference of comparison, and that is the stress strain curve we developed. So the last thing for about basic mechanical properties, we want to see people have done all different methods and try to improve the mechanical properties of the materials. What I say is, if you want to improve that, you should using a cheaper method. So using very expensive nanomaterials may not be the way to go. So what we did is we tried different method. We did a NaOH solution that the results indicate that's not a good option, because your NaOH is not cheap. And also after you're using this NaOH solution to wash crumb rubber concrete, the results is not really very good. There's not much improvement at all. And we also did some water wash, and this is a kind of a tick. Water wash is okay, and the results was even better than the NaOH solution, and it's cheap. You just need to wash it and get good results. So that is, this method is kind of recommended. And another method we did was a heat treatment. So what we did is we just we call them thermal treated crumb rubber concrete. So we're just using a common furnace. You see this one, the ovens here. And at a constant temperature of 200 degrees, not very high, just 200 degrees. And then we tried several different heating times, varying from 1 hour, 1.2 hours, up to about 2 hours. And in the end, we found out 1.5 hours provided the best results for the testing. So this is summarized some of the 28 compressive strength improvement. And you can see this is a reference group without any rubber, and this 10%, 20%, and 40% of rubber. You can see the red color is thermal treated samples. You can see the compressive strength was improved significantly, especially for the higher percentage of rubber of 20 and 30%. That can increase really from about 13.7 megapascal to nearly more than doubled, up to about 31 megapascals. So we thought this heat treatment is a kind of economical, cheap, and simple way to improve the properties of crumb rubber. And this work also published in Construction and Building Materials in 2019. So that is some very interesting results. So this just summarized. We have done a lot of research. So if you are interested, you can read our paper. So here just summarize a few mechanical properties of crumb rubber. So another thing I want to see is the durability, because durability is really important. If you want to use crumb rubber in the concrete products, you have to test all the durability performance of the crumb rubber concrete. So in the literature, most research more focus on the high strength concrete. So we just try to see what happened for the normal concrete. So why we have to work on the durability is because as I said, a lot of research was more focused on the mechanical performance of the strength, and we want to understand how the crumb rubber concrete deteriorate. Is different to the conventional concrete, or is quite, or it's no different. The performance is similar to the conventional concrete. We don't know. That's why we need to find out the answer. And the research, as what I said, was quite limited. Major research was limited on the low water bundle ratio. So that means they produce very high strength concrete. Because our research is more focused on the residential construction, and we know for residential construction, the compressive requirement is very low. So it's about 25 megapascals. So that's why the durability test we're doing was more focused on the low strength concrete, not in the high strength. And also the results people got was quite inconsistent for each different durability performance. So that's why more research was required. And also they have different tests and different rubber contents. So for example, you see some, this is just some testing here. We tried 3 different properties for the durability testing. We have using the purely Portland cement, and also we're using 10% of rubber, and also using some percentage of the flash, and this one using some percentage of slag, and with 20% of rubber. So that is the basic compressive strength, and based on that, we did a durability test after that. So what test we did? We did a water subjectivity test, which is called a liquid ingress. And we did a chlorine ingress test as well to look at iron deficiency or left analysis. We did a carbonation test, and also we did abrasion test as well to see the wear resistance if you want to use them as a pavement. So these are the 4 major durability tests we perform. Okay, so what concrete, as I mentioned before, we have low strength concrete, 20 megapascal. We also did a medium range, 32 megapascal. For comparison, we did high strength 50 megapascal as well. And for the bundles, I said we have 100% Portland cement. We have another group of samples with 20% flash, and another group with 30% of the slag. So we have 3 different groups. And for the rubber content, we have 10 and 20% by volume. So these are all the mixed designs we did for the durability test. So the first one, we look at the water subjectivity test. So this subjectivity test is known as penetration of liquid into porous matrix under unsaturated conditions and associated with capillary suctions. So we only show the results of the middle range concrete strength, which is 32 megapascals group. So in this group, the mix 31 shows slightly lower water subjectivities at old age tested when compared to the control mix, which is M30. So M30 is M30, 33, and 36 are the 3 control mix. Then because we have 3 groups, remember we have 1 group of flash, another group of slag. So that's why we have 3 groups, normal 1 flash and slag. And for each group, we have corresponding 10% crumb rubber and 20% crumb rubber. And then we have other groups as well. So that's 28 water subjectivity results. As I said, we use a higher bundle ratio of 0.61. The compressive strength is 32 megapascals. And 28, 56, and 91 days. So that's its results. So you can see, as what I said, mix 31, which is 10% of crumb rubber, it shows a slightly lower water subjectivities at all ages. So that's very interesting results. However, the mix 32, where you see 20% of the crumb rubber, they did show a lower water subjectivities, but then is higher, a lower subjectivity at 28 days, but that will be higher for 56 and 91 days. So that's 26 days. You see this M32, this yellow color, then is be lower initially 20 days, but that will be higher and a little bit higher for 56 and 91 days. So both M34 and M35, that is 10 and 20% with fly ash mix. And you can see for the 34 and 35, the trend is very similar to mix of 32, so the flash effect is not that significant. And mix 37 and 38, they all show a higher water solubilities and then the control mix at all the ages test. So this trend appears to be approximately very linear increase in water solubility and the rubber contents at 28 and 91 days test. But this not really occur for 56 test where the water solubility for the mix, which M37, that is 10% of rubber, is higher than the M38, which is 20% of rubber. So this is a big inconsistent results for this, the blue color, but all others following the same trend where you have a higher rubber contents and the water solubility was a little bit higher. But even said all this, we can see there is no significant difference about water solubility compared to the control sample, even at 91 days. Another test we did was the chlorine test. So we're using the modified NT-BIOT 492 method, and we did accelerated test for 24 hours duration, and we use electricity to push the chlorine ions into the concrete. So that is the testing results for the lower strength, 20 megapascal, and that is for the medium strength of 32 megapascals of all these three different group of the testing. Okay? So the mix is very interesting. The mix with supplementary cementitious materials, so that is M23 to M28. So those 23 to 28. So we're using either slag or using flash or slag. You see these groups show a clear reduction in chlorine equations with age. So the band type show really a significant impact on the chlorine mitigation coefficient, but the crumb rubber results effect is not really that significant. So that is, say, for example, that is, I look at 56 days. That is normal mix without anything. So that is with 10% rubber. You can see increased the durability increased a little bit if you're just using normal Portland cement, and but at 98 days is slightly reduced. It's pretty consistent, but a little bit higher than the mixed designs. For the 20% of rubber, actually you can see there's no difference at all, not much difference, even lower. So it's not a problem for chlorine. But if you look at using the flash, you look at M23 and M24. So you can see by using the flash, the mitigation coefficient quite reduced compared to the normal Portland cement, and even reduced further when using slag. So you can see the cementitious material did improve the durability performance of the concrete. Okay, so the trend is similar for the middle strength concrete. Is similar strength. Of course, the coefficient is lower. We all know when you have higher strength concrete, you get a denser structure, and of course, you get less the mitigation. You have less of the chlorine infusion. You get a lower mitigation coefficient. So this is well known. Another test we did was the carbonation test. So based on CIA test modified method, and we have 2% of CO2, which is 65% humidity and 25 degrees. With the test will last for about 6 months. So that is the results. We can see the lower strength mix on M21 and M22. So with 100% of total Portland cement, they show almost no difference in carbonation test compared to the control group of M20. So that is your M20, that is M21, and that is M22. So these very consistent. And even you have flash, the carbonation rate increased a bit, but the results with and without crumb rubber still very consistent for carbonation. And the same thing for using slag, and the results is pretty consistent. And the same thing applied for the higher strength concrete. So really, the carbonation effect, there's no difference about carbonation effect for the crumb rubber concrete. So the last one we did was abrasion test to determine the abrasion resistance. We're using a modified testing method based on the paper because there is no such testing method available for normal concrete. And from this test, we found out the all low strength crumb rubber concrete mix show an increase in abrasion index regardless of the band type or the age of tested. So this suggested that crumb rubber has a negative impact on the abrasion resistance. So you can see that is for the 20 megapascal lower strength one, you can see the average index actually 10% still okay. So when you're up to 20%, there is a significant increase. So that is probably only negative effect for the durability performance of concrete. So when you higher strength, you got probably similar trends. When you have 10% of rubber, still okay. But when you use 20% of rubber, there is a pretty big increase about abrasion index. So that is an active point about durability performance. Okay. So now is summary of our durability test for crumb rubber concrete. So the water sorptivity, chlorine ingress, and carbonation, all three has E2 difference. So the performance is very similar to the normal concrete. But for abrasion resistance, there is a significant difference. 10% still, 10% still okay, but when you increase to 20%, there is a big increase of the abrasion index. So that's the only problem. Okay. So further research is keep going on when we try to see the effect of size of rubber, and also even want to do the more even longer term of testing. Also, we are doing there is under this test is ongoing for the field trials, which we have made some real concrete slabs and to do the field testing trials of this crumb rubber concrete compared to normal concrete. So next topic I want to discuss is the structural performance of profiled steel reinforced CRC composite slab. As what I said earlier, because there's no reduction about threshold performance, so our research was more focused on the slab. So that we did all different slab testing, but the one I want to show you today is more focused on the composite, which using profile steel reinforced concrete slab for this special type. So after material properties has been extensively investigated, and we conducted 2 projects to study the structural performance of crumb rubber concrete, where the strength requirement for concrete is not very, very high. So the profile steel sheeting can be worked as a permanent formwork. So if you have the steel sheeting, it could be used as a permanent formwork. That is save you money. You do not need to have formwork anymore during the construction process, and also can safely carry the weight of the fresh concrete. So the target compressive strength for this testing is 25 megapascals. So that is a profile steel. We're seeing on cold form steel sections made by one steel and with different size of the profiles. And this is crumb rubber concrete. So the particle size we used was from 1.18 to 2.36 mils for the rubber mix. And we have a 20% by volume replacement of sand because previous material testing indicate when you have the rubber content more than 20%, there is not worthwhile using that. So the profile test was bond deck with only 0.75 mils thickness, very thin. You see very thin structures, and with 550 megapascal as the yielding stress for the cold form steel. So these are 2 group of testing we did. We have 2 different sizes of the coarse aggregate of 10 and 20 mils, concrete, cement, rubber, and water, and other stuff. So the CC is normal concrete, and CRC is crumb rubber concrete. So for crumb rubber concrete, we have replacement rubber, 20% of rubber to replace the sand. So we did some different testing. The first group testing we did was a push off and pull out shear bond behavior. So because you can do the full steel testing, you want to understand what the bond performance of these composite structures. And we did a literature review and found out 2 different testing was available, and one is push off and the other one is pull out. And we're not sure which one gave us a better result. That's why the both method was trialed, and we want to see the difference of the results. Okay, so so that is show you where we put the string gauges in the different locations, and these are all different type of the mixed designs, and we used, and then the result we found out about shear strength and also the maximum the bound displacement. Okay, so you can see as a longitudinal shear bound is really governs the load carrying capacities and performance of the profile steel reinforced composite slabs. So that's very important for the shear bound behavior. So before the full scale testing, we did all this testing of two different methods, and we can see both push off and pull out tests have been done by us, and the results was kind of compared. So tau 1 in this form, as what I said before, was the maximum chemical bond. You can see CRC got higher results. So that's normal one push, that's normal concrete, and that's crumb rubber concrete. You can see that for the crumb rubber concrete, this much higher the chemical bond tau 1 compared to the normal concrete. Okay. And another thing is tau R, which is the other one. So that is the residual bond. And finally, this is tau U is the ultimate bond. And you can see for the CRC, we got very similar result for the normal concrete. So that is normal concrete for the push 1 and push 2. And that is for the push test for crumb rubber concrete is consistent. And this is for the pull out. This is push in, and this is push off, and this is pull out. And again, for pull out results is kind of also similar as well. Sorry, similar here, similar as well for the ultimate bonding stress. Okay. And finally, S1 is the end slip and the maximum chemical bond. SR is the end slip and the residual bond. And SU is the end slip and ultimate bond. So you can see all the performance is kind of consistent for the push off test, but there's some issues for the pull out test here for these deformations. So we found out, as what I said, the maximum bound stress from each test is quite different between push off and pull out. So that's why we perform some finite element analysis as well to further investigate the reason. So that is the finite element model for the steel deck deformation, and that is the load deflection curve. So both push off and pull out test and compare with finite element model. So from this, we find out the pull out results, which is this scoop, because you can see they're not really fully consistent with the push out test. So we find out this the pull-out test is not really recommended for further applications because the global deformation of the steel deck increased the load from pull-out test and hence caused the overestimation of the bond stress. So that's why they got some very high bond stress analysis results there compared to the other one. So you got some high there. And the pull-out test setup tends to significantly overestimate the bond stress by producing higher deformation in the reps and also the softy of the steel deck. So therefore, if you want to perform the small scale composite testing, we recommend using the push-off but not using pull-out test. Okay. So that is the actual construction to this composite slab. That is before the concrete pouring. So we just had the formwork ready and just keep working, get formwork all set up. And then we got a concrete truck because we tried to simulate a real construction situation. So we didn't do any laboratory mixing. So we got a construction company who doing the normal real practical concrete mix delivers. And we asked them to have pre-mix of the crumb rubber concrete for us based on our mix designs and delivered to our laboratory, and that is a puring of these concrete slabs. Okay. So some more results you see that is puring of concrete slabs. So it's very interesting actually. In our small laboratory testing, we found out that the average slam was quite small. It's pretty sticky. The workability is not really good for the crumb rubber concrete. So we use a higher percentage of the rubber. But in the same mix design for the real constructions, it give us different story. So actually there's no workability at all. And the average slam was more than our calculations. It's reached about 100 it's about 170 mils, much more than what we're expecting. So that's some interesting difference from the laboratory to the real constructions. So here just show you some more construction procedures. This pure slab and that's final finish. You can see the final finish was pretty smooth. They really, and also in our small test in the lab, we found out some rubbers was floating at the surface of the slab. But for this real one, it's no floating at all. Everything was kind of very similar to the normal concrete. So there's still some construction procedures. Okay. So that is the testing setup. Of course, we did the normal 4-point bending test as shown in this diagram, testing setup and testing. So we have a longer slab and we have the normal concrete longer slab, normal concrete short span slab, and also we have the crumb rubber concrete with long span ratio and crumb rubber concrete with short ratio. So this we have two lines dual testing. One is 1.8, the other one is the 3.4 because we want to see the shear performance as well. So that's why we try two different lengths. And the shear span one is longer one is 800 mils and shorter one is half of 400 mils. So this is some testing results. So that is the this one is the 7 is the CC long slab, this long slab, and that is a CRC, the crumb rubber concrete long slab, and the red color is normal concrete with short slab, short shear span, and this is CRC concrete with the short spans. Very interesting results. We can see the composite slab with crumb rubber concrete had higher failure load, although the compressive strength was lower. That's my point, which I talked to you at the beginning of my presentation. So when we did the compressive, I didn't show the compressive result here, but it's in our paper. I think the compressive strength when using 20% of crumb rubber, it's reduced about say it's more than 30% reduction for the compressive strength, but this not really affect the flexural strength at all. So for both longer span and shorter spans, the compressive strength actually was higher. So that's why we say CRC is a viable option in residential composite slab constructions. So although you have lowest compressive strength, this not really affect the flexural strength performance ultimate loading carrying capacities for either a shorter span slab or longer span slab. So this is some results you see for the CRC L1 is maximum stress is up to about 22. So that is cracking stress was higher than normal concrete, and this is ultimate strength also higher, and that is for the short spans. So that is the cracking load was much higher, and this is ultimate load also much higher. So increase from 33 to 39. And with this, for this testing, we repeat for each test about 6 slabs, and we got a very consistent results. So that means although the compressive strength reduced, we have improved flexural performance of the composite slab. So next one I want to introduce you is another form of the structure element. So we're using the foam rubberized concrete as infill materials in profiled steel composite walls. So this one we did was composite slab, and here we'll make a foam concrete as infill materials. And we're still making the profile steel, but this time we make instead of making slab, we made the walls. So we try to make another product called lightweight foam rubberized concrete. So we have the preformed foam. You see this diagram for the foam generator. We have river sand. We have crumb rubber to partially replace the river sand, and we also have the cement. And we try to make a foam rubberized concrete. So that is the final product for the foam rubberized concrete. And we did all different testing, compression test, tensile test, and flexural strength test. All this being carried out. So here show you some testing results for the actual compression test. You see this is testing up for the composite walls and actual compression test. So we're using digital image correlation DSA to measure the strength and deformation of the whole surface of the steel sheet, and also using a software 3D package to measure all the deformation changes. And you can see from these two diagrams here, the steel strength distribution is more uniform and similar in the wall, and compare the one with the normal concrete. So the one with the crumb rubber concrete can give us more kind of uniform distributions, and also has less cracking and more ductile performance. So overall, the foam rubberized concrete can effectively consume recycled rubber particles from waste tires, and it is suitable option as the filler materials in profiled steel composite walls. So that is you see the difference between the normal test and the crumb rubber concrete test. So it has much more uniform distributions compared to the normal concrete. So this is with 20% or even more rubber content there. So that is kind of a Philly pattern of rubber concrete. And further testing was very interesting. That was the shear test. So after we did actual compression test, we did a shear test as well. So from the shear test result, we found out there's no significant difference in ultimate loading capacity and shear capacity for concrete panel. Doesn't matter what percentage of crumb rubber was used. So that is the diagonal deformation. You see that is diagonal load comparison. We have the no crumb rubber, 8% and 17% crumb rubber being used. You can see the performance is kind of quite similar. And ultimate strength decreased by about 6.2 and 12.9% while using 8.5 and 17% rubber under the monotonic load. So under static load, there is a reduction for the ultimate strength while you do the shear test. And but another test we did was cyclic test. So that is normal under monotonic load, and that is under cyclic load. And a very interesting result for the cyclic loading testing, because we found out compared to the static one-way loading test, the cyclic test results indicate the ultimate strength actually was not decreased, it's increased. It's increased by 10.3 and 8% when using the same amount of 8.5 and 70% rubber. So under the monotonic load, ultimate load capacity decreased, but under cyclic load, it was increased. You see this, the cyclic loading displacement, diagonal difference, and the loading performance, it is increased. Okay. And also the ductility was increased as well by about 19.1 and 14.9% for composite panel with 8.5 and 70% of rubber. So both ultimate strength and ductility increase while we have cyclic loading test. And the total energy also increased by about 13.6 and 10.7 for the composite panel, while we have 8.5 and 70% rubber as well. So the cyclic loads had some effect for the foam concrete panels, but it has good effect for the foam concrete panels with crumb rubber. So I say all this increase was for the crumb rubber concrete, but for the normal concrete, actually doesn't matter is under monotonic load or under cyclic load. The compressive strength actually under cyclic load, compressive strength actually was decreased, but for the crumb rubber concrete, it was increased. So that is a major difference about this shear test. Okay. So that is show you the diagonal displacement and also the load for the composite walls. And this is an envelope because it's more clear for you to see the envelope. That's no crumb rubber. That is the 8%. That is the 17%. That is the difference. Okay. And finally, we did some impact loading test. So that is normal composite walls for normal foam concrete. And this composite walls with up to 17% of crumb rubber in the concrete. You can see under the impact load test. And this one, the inside concrete was just smashed into pieces from testing. However, after you have the rubber increase as a crumb rubber concrete, foam concrete, for same impact testing, although there's significantly damaged, but the whole panel of the infill concrete is still pretty intact. It's not as smashed into pieces as the normal concrete. So that is a quite a good improvement for the performance. So this is testing setup. We have the big bullet just coming into the wall, and that is the result. Okay. So the last thing I want to talk about is from lab to slab. So to show some practical research work we done for this work, we call them from lab to slab. So before we're doing the real construction, we just here is some summarize of the work for practical Crumb rubber concrete. So we're using 32 megapascal control concrete, and 20% of the sand volume was replaced by rubber with the full commercially available rubber sizes, because we want to try and find out the optimal mix design. So the initial concrete slam and concrete strength were all measured. So you see that's its result. That is rubber size. This is the normal concrete, no rubber. That's using 40 mesh, 30 mesh, bigger size, 1 to 3 mils, even bigger size, 2 to 5 mils. And that is compressive strength. You can see very interesting results for 28 days compressive strength. So you have 40 mesh, compressive strength decreased to 24, and you have 30 mesh is about 25, and you have 1 to 3 mils decreased to about 25.2. But for the larger size of rubber use, 2.5 mils, and the compressive strength actually was higher, is 26 megapascals. Okay, so all of them have 20% by volume of rubber. And this is the slam test. So the control one was 105, then it reduced to 70 for 40 mesh, increase a little bit for 30 mesh, and increase speed of the 1 to 3 mils. And again, for 2 to 5, get us a very flowable structures with a good workability. I increase about 150 mils. So therefore, we find out 2 to 5 size of the rubber with 20% volume replacements was really the best results, and also is the cheapest results as well, because 2 to 5 mils rubber was much cheaper than the 40 mesh or 30 mesh. So this is just summarize some of the mix designs. So that CC32 is no rubber with 32 as a compressive strength. Then we're using 40 mesh, 30 mesh, 1 to 3, and 2 to 4 mils, and cement sand, 2 stones with different rubber contents replacement. And these are the testing results, which is summarized there already. And another important thing was the mixed order, because we found out the mixed order has big effect for the performance of Crumb rubber as well. So mixed order was also investigated to see the difference of workability of Crumb rubber concrete and normal concrete. And then the optimal mix design from lab to slab was practically applied to a 1 meter cubed of concrete using large concrete mix. Okay? So the conclusion from the laboratory trials was then practically applied. We use is 1 meter cubed of concrete from mix of CRC25 and for concrete and CC20R concrete to make sure that mix design worked well when using truck mixer from the concrete applied. The slam was measured 3 times for those mix, and the average recorded initial slam was 150 mils and 220 mils for CRC25 and CC20R mix. And also, they were even better than those observed from laboratory testing lab. That's why I tell you, when you have the large quantities and using the truck mixer, the workability actually was improved compared to the laboratory testing. And this is a real construction of slab. As I mentioned earlier, we had 2 slabs was constructed side by side, with normal concrete was with 20% of Crumb rubber concrete, and this is normal construction side and things, and this is during the curings. So the residential slab was purely at my university campus at Molson Lakes, which was in October 2018. So now it's already probably 3 or 4 years. And so this will just show the actual construction on the day. So the tool slab has been continuously monitored in the past 3 or 4 years, and the results was pretty good. Okay, so we did a hydration temperature test during the thing, and we did ash dampness test. We have beam dampness, carbonation test and edge dampiness, plastic removal before, and all the testing was carried out for both slabs. So here is summarize the results up to date. So the highest hydration temperature recording for the normal concrete was 33.2 degrees and occurred at 11.16 hours from the mixing completion. And for the crumb rubber concrete, we call them CC20R, was showing 27.9 degrees. So actually the hydration temperature was lower at the same time. And the recorded highest hydration temperature for the crumb rubber concrete was less and later than the normal concrete mix, with the maximum value actually was 29.2 degrees, occurred at 17.5 hours, but for normal concrete showing 30.7 degrees and at the same time. And CRC decreased the heat transfer rate with concrete mix and also less delayed hydration temperatures. This is some good thing. So up to 9 months, concrete age, the measured carbonation depth for both normal concrete and crumb rubber concrete was 0. And no visual deterioration was observed on concrete slab even up to now. And the monitoring for longer term was still continuing and keep going. So there's some good signs. So CRC, as a summary, CRC shows good workability when rubber was added and mixed dry and wet with other materials. A turbo mixer showed that better CRC strength than the pan mix, which is a promising observation, as turbo mix has the closed mixing mechanism to the concrete truck in practical applications. So while further testing are still being conducted, so these large-scale results provide a promising evidence that crumb rubber concrete has potential for application in the residential footing market. So the last, if I still have a few minutes, I will show you a 2-minute video to summarize about this project. But because when I show this video, I have to share a different screen. So I'll share this one and I'll share a different screen with you. I'll just try to share a different thing with you guys. I'll make this screen bigger. It's my thing. Do I have time, or just if no time, I can give you to do them later because I don't know how can I find my screen.
Ma'am, you stop sharing and share this.
I want to share the video, but I couldn't see the sharing screen with me, so I'm not sure where that is. I just close my PowerPoint first. Stop sharing. Don't see the full screen for some reason.
So yes, now we can see your screen. I think if you play anything, we can see. If you see play.
Yeah, but yeah, the thing is, I lost the share screen